Reactivity Series. You've known of its existence for a long time now, and you're kind of aware of where things are, more or less. I don't necessarily think you have to learn these off by heart and in the right order, but knowing that group 1 metals, potassium, sodium, and calcium, group 2 metal, which is quite far down group 2, so it's quite reactive, they find themselves at the top, and then down the bottom you've got copper, silver, gold, platinum. They're unreactive, and then in the middle your zinc, your iron, tin, and your lead. And where they are is going to affect how we can get them. So metals above carbon, because carbon is less reactive than these metals, they cannot be extracted by using carbon or carbon monoxide as a reducing agent. They must be extracted by electrolysis. So all of these metals are obtained by electrolysis. You know that from aluminium from last year. Underneath carbon, the metals can be extracted by the reduction of their oxides by carbon or carbon monoxide. So you can make these metals by using carbon and carbon monoxide, and we'll see that in a few examples coming up. Metals above hydrogen, all of them will react to produce hydrogen gas. So essentially they're displacing hydrogen from an acid and making hydrogen gas. And then metals at the bottom, below hydrogen, they exist as native metals, or they can exist as native metals. So they can be found as their actual metal in nature. Because they're so unreactive, they haven't reacted with anything else. So we can find them. This was the obsession, wasn't it, of a lot of mankind in the past. A lot of wars have been fought, especially over these two, silver and gold. So, some extra notes. We know that metals above carbon have to be extracted using electrolysis. The reactivity of a metal is how easily it loses its electrons to form positive ions. For example, potassium easily loses its electron, which is a long way out, isn't it? It's right out in the fourth shell, all on its own. It can be lost easily and it forms compounds readily. Whereas something like copper resists losing its electron, so it's not as reactive. It's more difficult for copper to do this, so copper is not as reactive. This means that reactive metals, when they do react, they tend to form very stable compounds, and it's hard to make them go back to become atoms again, which is one of the reasons why we don't find potassium and sodium as native metals. They've reacted, and once they've reacted, it's very, very difficult to get them back to being metals again. We need to use the electricity, which is why we didn't actually isolate them, make them, until only a couple of centuries ago, when electricity was invented. Okay, this stability affects the thermal decomposition of the compounds of the metals. So compounds of sodium and potassium resist thermal decomposition, and they are very stable. So you need to remember these patterns of behavior because you have to reproduce the equations that are related to these patterns. So for example, carbonates, if we strongly heat carbonates in a Bunsen burner, potassium and sodium do not decompose. All other carbonates, they decompose to give the oxide and carbon dioxide. So carbonates, we saw that with calcium carbonate before. It will give calcium oxide and carbon dioxide. Hydroxides, sodium and potassium do not decompose. All other metal hydroxides, they decompose to give the oxide and water. The oxide and water. Nitrates, sodium and potassium, this time they decompose a little bit to give the nitrite, which is the compound with the NO2 minus ion, and the other metal nitrates decompose to give the oxide, nitrogen dioxide, and oxygen. Let's have a little look at these equations. Okay. Have a go at the thermal decomposition equations for zinc carbonate, calcium hydroxide, sodium nitrate, and magnesium nitrate. Stop me here and have a try, following the rules on the previous table. Okay, zinc carbonate decomposes to form zinc oxide and carbon dioxide. There you go, and it's balanced. Calcium hydroxide decomposes to give calcium oxide and water. Notice it's in the gaseous form, but that's because you're decomposing it at high temperature. So steam is produced at first, isn't it? Sodium nitrate decomposes to make the nitrite, and it looks like that. Okay, so the nitrate becomes a nitrite. We have to balance that equation, so we need 2 and 2. And magnesium nitrate, well, this is a bit more complicated. It decomposes to give the oxide, nitrogen dioxide, which is a gas, there's a symbol missing there, and oxygen. Okay, so we need to balance this equation. Have a go. It's quite tricky. The magic number here is 4. I always remember there's a 4 before the nitrogen dioxide, and then everything else falls into place. 1 oxygen. Nitrogen dioxide is a brown gas. It's very clearly observed when you warm or heat these nitrates. And oxygen is a colourless gas, as you know, but you can prove its presence because it would relight a glowing splint. It's quite a nasty, acidic brown gas, nitrogen dioxide. Okay, we've just mentioned what's observed in this reaction. In this reaction, you wouldn't see very much. It's a white solid, white solid. This would relight a glowing splint. Here you would see water vapor coming off, and here you wouldn't be able to see anything. White solid goes to white solid, but this gas would turn lime water milky. Okay, try essential chemistry. The page is indicated.